Okay, so this is hss2381, the audio version of the bivariate analysis class, because the internet is not working today, and so we have to do this the old-fashioned audio way. Exciting. High technology. Isn't this great? So I'll stream the audio later on from my website, and that'll go on your website. So, hey. So if you're listening to the audio for the first time now, we've missed the first 20 minutes of the prelude to all this, but everybody in class got it. All right? So now we're moving on to the kinds of study designs that allowed us to get the data that we're going to analyze in a second. So you may have heard of some of these concepts before. If you haven't, great. We're starting from scratch. The first concept is a cohort design. A cohort design goes from forward in time. That's really what I like to think about. It goes forward in time. And the key attribute to a cohort design is you begin by ascertaining your subject's exposure status, and you follow them forward in time to see if they get the disease. In other words, if I'm looking at lung cancer and smoking, I ascertain whether or not you smoked first. So maybe you smoked, maybe you didn't smoke, and I'm going to wait 15 years to see which ones get lung cancer. And maybe a certain percentage of you get lung cancer, and a certain percentage of you get lung cancer, and I compare those numbers. That's a cohort design. The book calls it a prospective design. That's not a common terminology here. Prospective usually means forward in time. Retrospective means backwards in time. It's possible to do a retrospective cohort design, but let's not worry about that right now. So think about this again. A cohort means going forward in time. And it's defined as ascertaining exposure status first and getting the outcome later. The opposite of a cohort design is a case control design. A case control design is when you start by ascertaining the outcome and you look backwards in time to see what the exposure was. So in that scenario, I find some cancer patients, and I find some people who aren't cancer patients. And I look back in time to see which one of these guys smoked and which one of these guys smoked. And I compare those numbers. How do I look back in time in a case like that?
Health records.
Health records. Or what else? Health records is the most common version. What else can we do?
Interview them.
Yeah. Exactly. Or you ask them. It's okay. Just ask them. That's very common. So obviously there are biases implicit in those approaches. I can ask you and say, yeah, maybe I smoked. I don't know. Maybe. Sure. So there's some recall bias and stuff like that. But those are the two most common population health approaches for observational studies like this. There's a nuance here. If I am selecting my cases, by the way, is the word for the people with the disease. Okay, and the control is the ones who don't have the disease. So I'm selecting my cancer patients. So I got 100 of them. Great. I got 100 people who don't have cancer patients. Can I now compute the proportion of the population that probably has cancer? Why or why not? Can I estimate? So I got 100 people with cancer, 100 without cancer. Can I estimate the proportion of the total population with cancer? Look at the cohort example now. I got a bunch of people who smoked, a bunch of people who don't smoke, and I wait 15 years. Now, X% of you guys have cancer, and X% of you guys have cancer. Can I now estimate the proportion of the general population that probably has cancer?
I think it would work better with the case control.
Would it? Think of the nuance here. So because nobody's got cancer in the cohort scenario, and I'm waiting until a bunch of you do, well, that's reflective of the natural progression of disease in the general population. So I can use that information to model the experience of the entire population. So if 20% of my total subjects get cancer, probably that's reflective of 20% of the general population getting cancer. Because I didn't do anything, you guys. I just watched you. So you did it for 15 years, and 20% got cancer. Okay, so that's fairly representative of the general population. With the case control, what I did, I went out and I looked for 100 people with cancer. And I found them. And I can't do anything with that because I found you. I chose you. So I can't say that's a natural representation of the world. Right? That's a subtle nuance. So we say that in retrospective case control situations, we cannot compute incidence rates because it's artificial. I've selected my cases. But in cohort designs, I can, because it's natural. I let the cases manifest as they will. I'm getting ahead of myself here. So then we have experiments. What's an experiment? I'm going to go over this all again. So I'm just introducing it right now. What's the definition of an experiment? Do you know? Everyone thinks they know. And the lay public thinks about experiments all the time. But there's a specific definition for experiment when it comes to the health sciences. Any idea? An experiment is going to be a little bit different from what I just described. You may think that if I got a bunch of people who are smoking, a bunch of people who are not smoking, and I wait and see who gets cancer, that's an experiment. But it's not. An experiment has a certain characteristic that is different from what I just described. Any ideas? No? Did I make you smoke? Yeah.
Do you start off with a hypothesis and then
We can, but you have one for all the scenarios. Yeah.
in an experiment, you make something happen?
Exactly. Exactly. I interfere in experiment. I make something happen. Whereas, I'm getting off on a tangent here. It's no longer stats. We're into research design. But in the previous cases, we call those observational studies. I just sit back and watch what happens. I didn't make you smoke. You chose to smoke. I just chose to observe you. In an experiment, I will make you smoke. Right? So the most common experiment in population health sciences is a clinical trial. And that's where I got a bunch of you people, and I randomly assign you and flip a coin, you're going to smoke, you're not going to smoke, you're going to smoke, you're not going to smoke, until I got equal numbers. Then I watch you for 15 years, I make sure that you don't start smoking and you do, whatever the case may be, and then I compute, my rates. So is that ethical, what I just described? Probably not. I probably can't get some 5-year-old kids and randomly make them smoke for 20 years, right? So that's why it's difficult for the longest time to say that smoking causes cancer, because we couldn't do the experiment ethically. So we had to rely upon the observational data, which is very strong, by the way. So that's an example, an experiment. Poke a brain, something happens. So that's when the investigator does something and to elicit a response. So here is a clinical trial, or also called a randomized clinical trial. You have a study population, and I randomize into 2 groups. The first group gets the treatment, the other group doesn't get the treatment, or they get something called a placebo. What's a placebo? Heard that term? Yeah. The expectation part is the confusing part. Almost there. It's something that resembles the treatment without having anything functional in it that we're testing. So let's say I'm testing this new migraine pill. So you're going to get the pill and you're not. But I don't want you to know you're not getting the pill. So I'm going to give you a pill that looks just like the migraine pill. You're going to take it exactly the same amount of times as they take it, with the same amount of water and everything. It's the same color and the same size, but it has no active ingredient. Right? And that's in order to remove the biases that may arise. If you know you're getting a pill and you know you're not getting a pill, maybe you'll get better just by psychology. That's a placebo effect. Right? So placebo is a Greek or Latin? I was confused. I think it's Latin. For I please you. So it's like, ooh, I have this thing that doesn't do anything but pleases me. Anyway, off on a tangent. So that's a classic experiment. And the randomization, you learn more about that in your research design, is about making sure that biases are equally distributed. That's not that important. So here's one from the slides. Is let's say I'm doing an experiment to determine which is the better way of studying for the exam, reviewing the slides or reviewing the textbook. So here, the entire class, I randomize. Half of you are going to study the textbook only, and half of you are going to study the slides only. And at the end of the exam, we see who's got the higher marks. Right? Easy. So, like I mentioned, cohort is you follow people forward. Case control, you look backwards. And an RCT is the classical experiment that everyone thinks about. So cohort, it originates from the Roman cohort, which was actually a unit in the Roman military who always moved together, forwards in time. Right? You begin with an exposure. So you select the subjects based upon whether or not they have the exposure. Some smokers versus non-smokers. Okay, here's an example. Well, let's ask you the example. Let's do it here. So what are ARV drugs? Have you heard that term, ARVs, for HIV patients? It stands for antiretroviral drugs. So HIV patients take ARV drugs, but they have a lot of side effects. We want to know whether or not one of the side effects is nausea. So in the cohort milieu, the way you define it is you look at a group who's taking antiretroviral drugs and a group that isn't, and you follow them forward in time. How do you follow them forward in time? There are two ways. Any ideas? Without the time machine, there are two ways of following a group forward in time. One way is obvious.
Like, are you looking to speed it up?
I could. The obvious way is not to speed it up. I could sit here and wait. That's the other way. No. The other way is to start with medical records. Right? So if I have a bunch of hospital records and people going back 25 years ago, oh, here's some people taking ARVs. Here's some people who are not. Now look forward in the literature to the present day to see who got nauseous. So I can do that instantaneously. I'm moving forward in time, but I'm doing so in the past. We call that a retrospective cohort, whatever. The point is there are creative ways of doing it, but every time we're looking forward. And this example, we begin with finding people who took the medication, finding those who didn't, and look forward in time to see how many got nauseous. Okay. So here's the, let's take the experiment example we did last time. So if I'm trying to figure out which is a better way of studying for the exam, slides versus textbook, how do I design that in a cohort methodology? Yeah.
You find people that are going to study just the slides and find people that are going to study just the textbook and then wait to see who does better.
Exactly. Now, how is that different from the experiment?
You didn't assign people to study.
Exactly. They chose themselves, right? Okay, exactly. So case control is the same thing. So case control, again, I mentioned you start with the outcome and you look backwards in time to see what they did. So in the case of the antiretrovirals, how would you design that same experiment in the case control methodology? Remember, the antiretrovirals is I'm trying to find association between taking these drugs and becoming nauseous. So in a case control environment or methodology, I begin by ascertaining the outcome. What's the outcome of the disease? Nauseous, exactly. So I find some nauseous people and some who else? Exactly. I look back in time or ask them, did you take ARVs? Now, right away, you can probably tell. If I find a bunch of you in the audience, who was nauseous today? It's probably a couple people. I ask, how many of you take ARVs? I ask, people who aren't nauseous, how many of you take ARVs? Probably none. Maybe there are, I don't want to know. That's a violation of your privacy, right? Probably none of you are taking antiretroviral drugs, maybe one or two. So automatically you see that there are pros and cons to using these methods depending upon how common these diseases are, right? So if a very rare disease, it's probably not wise to use a cohort example. All right, here it is. That's the example I just gave you. So smoking associated with lung cancer, I find some lung cancer people, some non-lung cancer people. I'll look back in time to see who smoked. All right, here's an example. Here's a study that looks at 6 people with Creutzfeldt-Jakob disease. What's Creutzfeldt-Jakob disease? Who knows what that is? Creutzfeldt-Jakob disease? It's one of the sexy ones. Something to do with the brain, that's true.
It's from bacteria or virus.
It's not for bacteria or virus, a third kind of, it's not for a parasite. It does, yeah, but it has a common name in the lay parlance. It's mad cow disease. It's human mad cow disease caused by a prion, not a bacteria. Okay, so it's a very rare disease. So everyone writes that down. I'm not testing you on pathology. Don't worry about that. Right? So you have 6 people with Creutzfeldt-Jakob, 10 without it, and we look back to see how many are exposed to the Subway Santa Fe chicken sandwiches. Right? What kind of study is that? And what kind of study is that? What kind of methodology? Case control. Why is that? Looking back in time, and you begin with assessing the disease status. That's kind of the key to it. What do you begin with? Assess the disease status. This is a case control. Okay? So now let's go to the risk assessment now. Absolute risk is the actual amount of risk associated with each exposure status. So what's the absolute risk of getting cancer if you smoke? What's the absolute risk of getting cancer if you don't smoke? What's the absolute risk of doing well in the midterm if you study the slides? What's the absolute risk of doing well in the midterms if you don't study the slides? There's a subtle nuance there. If I ask you what's the absolute risk of getting cancer if you smoke, right away your mind translates as what's the absolute risk of getting cancer by smoke versus non-smoking. That's not what I'm asking. That would be a relative risk. The absolute risk is just if you smoke, amongst those who smoke, how many get cancer? Okay, that's the absolute. So it's not that useful of a risk index. It can be misleading. I was at a dinner party once, and some woman next to me is on some tirade about pornography or something. And she says, "Do you know that every single sex offender in jail looked at pornography?" And because I'm an asshole, I responded with, "Yes, and they probably ate bread as well." Doesn't mean that bread causes, But so what she was quoting there was an absolute risk. The exposure was looking at pornography. The outcome was being a sex offender. What she was missing was the flip side, which is what? The other absolute risk measurement, which is
How many people look at porn and don't become
the other one. How many people don't look at porn and become sex offenders, right? That's the other absolute risk you have to compare. So she was quoting an absolute risk, not a relative risk. It's the relative risk we care about. But to compute a relative risk, we need an absolute risk. So relative risk is like the ratio between two relevant absolute risks. Yeah, wasn't a good dinner party. Went downhill from there. Okay, so here is our contingency table. And this is what you'll be making every time you do this. Okay, so the exposure status is here. The outcome status is there. You can't really see it well. It's in yellow. Outcome, yes or no. Okay, there are really only 4 things on this table. They're in red here. A, B, C, D. And we label them that way, A, B, C, D. That's important because the formulas will be relative to A, B, and C, and D. Okay, so remember again, the exposure goes here. Smoking, yes or no. Cancer, yes, no. The exposure is the thing that causes the disease, causes in quotation marks, right? And we have the column totals here and here, the row totals here and there, and the total here and there. What is the N of this set of data? The N, of course, is the total number of people in my study. Express the N to me in terms of A, B's, C's, and D's. If N is everybody in the study, and these are the people in my study, what's the N? Yes? There it is. Not difficult questions. That's my N. Okay? So, here is some hypothetical data. We have a cohort going forward in time. We're going to follow 100 smokers and 100 non-smokers. These are my exposure status, right? We know because I'm starting out with ascertaining exposure, it's a cohort study. We also know it's a cohort study because I called it a cohort study. Yeah, see, this works. Okay, we follow it for 10 years to see who ends up with lung cancer. And these are my data. Okay? Straightforward. So my total is 200. We have 200 who smoked totally. We have 100 here. Oh, so there are 200 who we looked at, 100 who smoked, 100 didn't smoke. 85 got cancer, and 115 did not get cancer. I can barely see that. Okay, but here's how they splay out there. Now, the same number? What's this? What is this there? Oh, and my other example is this. So we're going to go through both examples. The second example has to do with using a needle to do some kind of aspiration thing, and we're trying to figure out which size needle has the most amount of pain or swelling, I think. So here we got a 16 millimeter needle and a 25 millimeter needle. So our exposure here is these 2 needle sizes. Our outcome is, was there swelling, yes or no? We can do this for any kind of question with 2 levels, dichotomous levels. Again, these are nominal data with dichotomous levels. Is this nominal or ordinal or something else? What is that? The needle size. You think it's nominal? You're so funny. Yeah, there's an argument to be made that it's nominal. I would accept that. because, frankly, it doesn't really matter that it's ranked. But yeah, 25 is bigger than 16, so we can rank it. But how we're using these data, I can see the argument for normal, so I would accept that. Okay, so the absolute risk is the proportion of people with a yes outcome. So, and we have two absolute risks in these data. We have those in the exposed group and those in the non-exposed group. The exposed group are the ones who smoked. The non-exposed groups are the ones who didn't smoke. Expose, right? So in the needle example, do I have the actual slides here? Come on, show me about the slides up. I guess I didn't. Oh, geez. Okay, for the needle examples, go back a second. So the absolute risk for those who got the 16 millimeter are 20 divided by 100, 20%. So 20% of my exposed group here got the thing. So that's my absolute risk. Here, it's 10%. That ain't hard. For the cancer one, 75% of my exposed group got cancer, and 10% of the non-exposed group got cancer. Right away, you start looking at the differences and realize, wow, the risk among smokers is so much higher than the risk amongst non-smokers. That starts you thinking, well, maybe there's something going on here. For this one, the risk really isn't that much different. So maybe there isn't something going on there. What do I do with those numbers now? Okay, those are absolute risks. So, first thing I want to look at is the absolute risk reduction, and that's the difference between those two numbers. So I'm subtracting the absolute risk in the unexposed group from the absolute risk in the exposed group. So in the needle example, it's 20% minus 10%, it gives me 10%. Therefore, there was a 10% reduction in the risk of swelling. We could argue. In the case of the smoking one, if I go back to the numbers again, what's my absolute risk reduction? 65%. So in that case, not a reduction, it's an increase. There's a 65% increase in risk caused by the smoking. Okay? That's actually not a very useful statistic. We put it here because we compute it and it's in our reports and all that, but that's not the go-to statistic. The go-to statistic is going to be the relative risk, and that's what we're doing next. The relative risk is just dividing the two, those two absolute risks. Straightforward. So in the needle example, it's 2. Now, you may ask yourself, what's a high relative risk? A high relative risk is like 1.5. It's like saying the risk of being exposed to this thing is 1.5 times, it's 1.5 times greater of probability of giving me the outcome than not being exposed to this thing. That's pretty high. So public health officials, if the relative risk of something is 1.5 times greater, we tend to take that seriously. Anything between 1 and 1.5, actually, we look at pretty carefully. 1.5, wow, where you sets off the alarms. So 2 is pretty high. For the cancer, where'd my cancer example go? How come? Where's that? Oh, this is my cancer example. It's the same data, by the way. So here the relative risk is 75 over 100 divided by 10 over 100. That gives me 7.5. 7.5. That's huge. That's enormous. So the relative risk of smoking relative to lung cancer is enormous. These are fake data, but it's not that far off. In fact, the real data are actually quite higher. And this is the kind of stuff that was presented in the court cases in the 80s or so, back when they're trying to determine whether or not tobacco companies were liable. In fact, I was offered a job once defending these big companies that are being sued. So I would work for a consulting firm in Washington. And so your job at that point is, as an epidemiologist, to sit on the stand and help the lawyers say, well, there's no actual causal data here. There's all associations, there's all correlations or relationships. We can't take some 5-year-olds and make them smart. It's really easy to pick apart these arguments. I didn't take that job, but if I had, I asked myself, how would I sleep at night? And the answer was, on a bed of money. And I chose not to. Kind of regret it. But there are I call the epidemiological hitmen. They bring you in to do shit like this. Anyway, so what if your relative risk is 1? What does that mean? How do you interpret that?
Not that high.
Not that high is true, but it's not precise. There's something very special about 1. Yes?
It's neutral.
It's neutral, so nothing's happening whatsoever. Okay, what if it's less than 1? Let's say for my smoking example, smoking and cancer, I got a relative risk of 0.5. How do you interpret that? It's better to smoke than not to smoke. It's protective is the term. And in fact, there are diseases like that. Instead of lung cancer, had I chosen Parkinson's disease, yeah, smoking is protective against Parkinson's disease. Smokers have a slightly lesser chance of getting Parkinson's than, I think it's Parkinson's. Might be a dementia, I'm not sure. Okay? So anything less than 1 is protective. Greater than 1, it's associative. I don't want to say causal again. It's associative. So 1 is that magic line. Anytime you divide two things that purport to measure the same thing, 1 is the magic number. 1 is the point where nothing happens. So ratios. Ratios are always around 1. Okay. So, we have here. Okay. So now we have this thing called a relative risk reduction. So we have absolute risk, we have relative risk, we had risk reduction, now we have relative risk reduction. Whew, a lot of stuff. So that's a proportion of the baseline risk that is reduced through non-exposure. Hey. So that's going to be our absolute relative risk divided by the absolute risk in the unexposed group. Wow, that's a lot of stuff going on. So we had computed that in this example here, the absolute risk reduction was 0.1. That's when we subtracted the risk in our unexposed group from the risk in our exposed group. We got 0.1. That's the ARR. Now, what I'm saying is, if I divide that by the absolute risk in the unexposed group, I get this other number. So that tells me how much the relative risk was reduced by the thing that I did. It's not that useful. It's hard to interpret. We rarely use it in my experience, but there it is. So just memorize the formula and plug it in if I ask for it. Otherwise, it's no. Yeah, I will never ask you to interpret this because it makes no intuitive sense. Okay. So the smoking example is the same thing. We take our absolute relative risk, which was 0.65, you compute it for me, and divide it by the absolute risk amongst the non-smokers, and I get 0.5. And that tells me that I was reduced by that much, which is 1 over that. Okay. The next thing we're looking at is odds. Remember I mentioned that you couldn't compute the incidence of something in a case control method because I'm choosing my cancer patients, therefore I don't know whether they are representative of the general population. A risk is just an incidence. That's all it is. So I can't really compute risks or relative risks or absolute risks when I'm using case control designs. I could, the numbers are there, they don't mean anything. So when I have a case control design, I have to compute something else, and that something else is called the odds ratio. So I'll say that again. So I said earlier that when I use a case control, which is when I select my cases, my disease people, I look back in time, I cannot use that information to assess actual risk of getting disease because I've chosen my disease cases. It's artificial. Therefore, I need something else to estimate risk. I'm still going to make a contingency table, and you can still type in those numbers that compute the ARs and the RRs and all that stuff, but it won't mean anything. So when you see a case control example, you know not to compute those things. There's only one thing you can compute, and that's this thing called an odds ratio. So before we do an odds ratio, we have to ask ourselves, what do odds mean? What are odds? Have you ever heard this term before in high school? So my professor is odd. No, I'm that kind of odd. A different kind of odd. Odds versus even. Okay, here it is. You know what probability is? We talked about it last time. Probability really is the proportion of an outcome over a set of possible outcomes. So let's say there are 100 of you, and there are 30 women. What is the probability that if I select one of you at random, I get a woman? Wow, just last week. It was Wednesday. 100 students, 30 are women. What's the probability that one of you is a woman? I'm not going to say it. 30%. That is correct. 30 out of 100. Straightforward. What's the probability that you're not a woman? 70%. Now, here's the hard part. What are the odds that you're a woman? In the lay media, we use these terms interchangeably. They mean something very different. The odds are defined as the probability of something divided by the probability of not that thing. In other words, the probability of something divided by 1 minus the probability of that thing. So the odds of one of you being a woman is 30% divided by 70%. Right? So here's an example. 80% is female. Odds being female. So if it's 80%, I use 80 in the example for some reason. The odds is probability over 1 minus probability. So 80 over 20, which gives me 4. So the odds are 4 to 1 that you're a woman in this case. That's how we get the odds in horse races and things like that. Okay? So what I'm going to do now is compute the ratio of odds rather than the ratio of risks. Okay, I'm looking around, everyone looks kind of confused or bored or something, so hopefully you're still with me. We'll see. Right. Oh, geez. Once again, my tables are kind of skewed here. Damn you, Google Slides. Okay, so the odds, let me scoop ahead. Okay, here we go. How come that's not working? There should be some stuff you can see there. The contingency table should be visible there. So visualize the contingency table. Here we have, let's say it's smokers, and here we have cancer. Cancer, yes. Cancer, no. Smoking, yes. Smoking, no. So the odds of a smoker having cancer is going to be that divided by that. It's the other way around. Okay? Back up a bit here. These slides are screwed up. Why are these slides screwed up? Okay, come on. Oh, sorry. Okay, let's back up a bit. I sent you the wrong way, sorry. The odds are going to be that divided by that, right? Okay, because that's our probability. Our probability is A divided by A plus B. The probability of not being A is B divided by A plus B, so the odds is A divided by B. Whew. Still with me? Kind of maybe, sort of maybe, kind of, sure, all right. I'll say it again. This should be smokers, and that should be like cancer patients. The odds for this one is going to be A divided by B. The odds of this is C divided by D. So the odds in the exposed group is that divided by that. The odds in the unexposed group is C divided by D. I can divide those two numbers to get the odds ratio. I can divide A over B divided by C over D. That's my odds ratio. What I'm trying to get to is that there's a faster way of doing it. And the faster way is to do the cross division. So A times D divided by B times C. If you simplify that complicated formula, that's what it comes down to. So in many ways, even though the relative risk is better, odds ratio is easier. So in practice, we kind of jump right to the odds ratio just to have some fun, right, and make our lives a bit easier. But the point of doing an odds ratio is it estimates a relative risk. It's another way of getting, well, the ratio of risks in a situation where the risk doesn't mean anything. It doesn't always estimate the relative risk. It only does so in a specific situation. And that situation is when the disease is rare. Most of the time, the disease is rare. And by the disease, I mean the outcome. The rarer the disease, the more likely the relative risk is to resemble the odds ratio. So a situation where I'm looking at whether or not smoking causes femaleness, I don't know, in this population, which is a ridiculous thing to measure, but femaleness is not uncommon in this population. So an odds ratio there will be very, very unlike the relative risk, and it's not the appropriate way to estimate it. What's rare? Well, That's a matter for debate. So we have these cutoffs that determine what rare is. Don't worry about it too much. Just remember that rarity is important. So here in the example from our smoking example, again, I'm sorry about the slide. I don't know why they didn't come up here, but that should say smoking, non-smoking, lung cancer, not lung cancer. The odds ratio is that divided by that, 2.25. If you remember, our relative risk was like 7.5, so they're not very similar. That's because lung cancer is not that rare in this particular situation. Okay. So here is, again, our odds ratio for the true data we looked last time. That divided by that gives me 27. Can't see that. All right. Which is better, the odds ratio, relative risk? I mentioned relative risk is preferred. It's more meaningful. It's more precise. But the odds ratio is an estimate. You can't compute a relative risk for case control studies, so we use the odds ratio to estimate the relative risk. So, that's a lot of stuff. One last concept. You with me so far? Did I confuse you? Sorry about that. I stumbled a bit. All right, one last concept. That's the number needed to treat. The number needed to treat it's how many people need to not be exposed in order to prevent one case of disease. So how many people in my population need to not smoke in order for the number of lung cancer patients to go down by 1? Okay. Useful statistic or index with randomized controlled trials, or trying to figure out, how effective our drug is, how many people need to take the drug in order to reduce our cases of migraine by 1, So it's defined like this. The number needed to treat is 1 divided by the absolute risk reduction. If you remember what the absolute risk reduction was, it's when I subtracted those two absolute risks. So once I subtract those two things, I divide them into 1. That gives me the number of patients I need to keep off of the smoking in order to save 1 patient. Right, so here's a case of the smoking example. I do the math and I get 0.65 as my absolute risk reduction for us earlier. So my number needed to treat is 1.54. So I need for 1.54 people to not smoke in order for there to be 1 fewer case of lung cancer. Does that make sense, 1.54 people? So if you're writing a report for the government, and the government says, how many people do I need to give up smoking to save 1 life? And your answer would be what? 2, exactly. Because there are no such thing as 0.54 people. 1 is too few, so the answer is 2. Clear on that? Yes?
Do you always round up?
Yes. Even if it's like 1.1 or 1.01, you round up. Because if it's 1, it's much too few. It's not enough. Okay. So I mentioned that, I'm repeating myself here, relative risk, you can't use it for case control. They are very similar, but they diverge when the risk is being computed for rare diseases. Hi, that's a lot of stuff today. Confusing stuff, sorry about that. Any clarity I can offer you? Any last bits of grayness? No? All right. So that's the homework, and I will put this audio clip on my website, as I mentioned, and we'll try to get this internet fixed. God damn it.